Hi, this is AC's 8-Bit Zone. My first computer was this TRS-80 Color Computer 1. Today, it will receive a hardware upgrade to support sprites similar to, but even better than, the Commodore 64s. While we're at it, it'll also get SID-style sound hardware for 4 voices. All of this is done in a small board that I call Coco DV that fits into the video display generator socket. You may be surprised that hardware and software are still being created for these machines, but it's true. There's been a steady stream of retro activity since the 1990s. And in the same vein, the hardware shown today will be available for all Color Computer 1 or 2 models. That is, as soon as the global FPGA shortage is relieved. But let's not get derailed by that right now. In the entire line of color computers that spanned the 1980s, there were no dedicated ICs or integrated circuit chips to handle sprite graphics or waveform-based sound. The Coco had the VDG for video, and it was drawn by pixel mapping. It had a DAC for sound, but the microprocessor had to manually generate the individual points in a sound wave. Other computers of the age had chips to offload these tasks from the microprocessor. The Commodore 64 had the VIC-2 and the SID. The Atari 800 line had the Antic and GTIA for graphics and the Pokey for sound. But on the Coco, if the programmer wanted to move Pac-Man or the Ghost, several bytes had to be manipulated for each object, as you can see in my previous episode. When a note or sound effect needed to be played, each point on the audio waveform had to be individually written to a DAC. That was a digital to analog IC. Now, contrary to what you may be thinking at this point, the Coco was always a joy to use for playing video games and learning to program with BASIC. However, I always wished that it had some of the graphics features of the Commodore or the Atari. For this episode, I chose to recreate the C64's Sprite hardware because I was so impressed by its capability. I also made a 4-voice version of the 3-voice SID. This Coco DV board adds all this, but it's completely backward compatible with the original Coco. The graphics and sound updates are optional to use for new games and basic programs. What could hardware sprites do for the Coco? Well, here was an early Pac-Man clone called Ghost Gobbler. It isn't even close to the actual game mechanics or graphics, but the game programmer had a lot to overcome. Each sprite had to be handled by dozens of computations byte by byte. As we saw in my previous videos, it is slightly tedious, and it slows the performance of the powerful microprocessor. The processor, by the way, is the MC6809. Now let's see what can be done with dedicated sprite hardware. First, let's see the Commodore and Atari versions of the game graphics. Here's the C64 version of Pac-Man. I feel sure that it's using the Sprite hardware. The sprites are 1 color each. The colors are slightly muted, I think, compared to the Atari version. Next, this is the Atari 800 version of Pac-Man. The sprites are still made in 1 color, but the colors are a little more vibrant, although still not true to the original game in the arcade. Now I'll show you my recent progress with starting to use Coco sprites and SID sound. This has been quite a journey for me. Although I've written assembly code for other platforms, this is my first for the Coco or the 6809, or even for a game. So here it is. Let's freeze the game right here. Now, I won't go on too much about this, but I wanted to mention this YouTube channel. It takes a lot of time and energy to make these videos. Please show your support by subscribing to the channel. I do not make any money from doing this, and subscribing is no cost to you, and it encourages me to make more and better content. And that's all I'll say about that. So back to this game. Programming it is in process. So far I've coded joystick control of Pac-Man and eating the pills. I've made the ghost algorithm for the motion as true as I can from articles that I read on the internet. I still need to add an attract screen, the blinky power-up pills, and other nice features like the interlude scenes between the levels. And one really important feature is that ghost collision with Pac-Man is disabled right now, so he'll pass right through the ghosts. You're only seeing a portion of the capability of this new hardware. In a later episode, we can talk about background scrolling, sound generation, and a new graphics mode that I'm contemplating. Today, we'll just get introduced to the Sprite features. How is this even possible? Well, the Coco's video display generator has been recreated in an FPGA. The board is called Coco DV, or Coco Digital Video. Here's the Coco DV installed in a Color Computer 1. Color Computer 1 was released in 1980. Now, I've pored over the Motorola datasheets and various posts online to determine exactly how the VDG worked and recreated that behavior so that it behaves identically to the original VDG. Well, and also to the updated VDG, the T1 version. Sprites and sounds are available through an unlock feature that new games may take advantage of. Now, what are the capabilities of the new Sprite hardware? It's actually hard to even know where to start. Well, as I said, I was inspired by the C64, which supported 8 sprites. Those were 1 color in high res, or 3 colors with half of the horizontal resolution. Coco Sprites will support up to 128 sprites stored in a new area of 16K of RAM. Up to 16 sprites are available at one time, and each one can be rotated through 8 indexes to use all 128. The sprites are always in the highest resolution and in 3 colors plus transparent. The palette itself has been updated to allow 16-bit colors. The palette can be reprogrammed with any 16 colors that you'd like with those 16-bit type of values. Sprites can then use any 3 colors chosen independently for each sprite from this palette. Having 128 sprites with up to 16 available at a time provides tremendous flexibility in the game programming. For example, in Pac-Man, the ghosts each have 8 possible looks. If you think about it, it's the 4 directions of travel, looking left, right, up, or down, and then the shimmering effect in the tail of the ghost. So that's 8 total variations of the ghost. So with one of the 16 sprites, you can load all 8 images of the ghost into the Coco DV. And then during the game program, you simply rotate the sprite index through 0 to 7. The power of sprites is that all the pixel drawing and storage into RAM is done before the game begins. All that the program needs to do is update the X and Y coordinates, or the sprite colors possibly, or the sprite rotation. All of these settings are contained in 4 bytes. The 4-byte field can be updated whenever you want, and it can be written from a basic program or machine language. It's always best to make the updates during vertical refresh, as we saw in the previous episode, and this is still true with sprites. The visual impact of hardware sprites is obvious, but now what is the effect on the loading of the processor? Remember when we implemented software sprites in the last episode? We were modifying 45 bytes of graphics at a time to move 1 sprite. There were 1 to 2 times that many calculations required to either AND and or XOR the bytes. And just think, every byte that we needed to manipulate required 1 instruction to load and another to store the calculation. Now that we're only calculating sprite locations, and we're letting hardware handle the rest. To visualize the processor loading, The idle routine paints an idle bar in the lower left corner. Let's compare the idle levels for an empty main loop, then a software sprite loop, and finally a hardware sprite loop. The higher the bar, the more idle time. First, with the empty game loop, we'll call this the 100% idle level. Now let's run the software generated sprite from episode 2. Just eyeballing the level, it looks like about a 25 or 30% reduction in idle time. So the processor is about 30% loaded. And finally, with hardware sprites. You see some jitter that depends on the code branches in the wall collision calculations, but overall the loading is minimal. It appears to be just a few digits percentage, maybe 5% or so. I've made my point about processor loading, but before we go, let's see the loading with the ghost routines running. Well, there's so much more to discuss, and we'll get to it in future episodes. This has been part 3 of the Sprites and Gaming series. Thanks for watching, and I'll see you next time.